You should now understand what we mean by planning in AI. Next, we will formalize this understanding of planning by means of a conceptual model for planning. This conceptual model will be a state transition system. Before I introduce the conceptual model that underlies planning, I want to talk to you about conceptual models in general and why they are a good idea. So what is a conceptual model? A conceptual model is a theoretical device for describing the elements of a problem. What this means is it helps us to formalize the problem we are trying to solve. This is good for a number of things. For example, we can explain the basic concepts with this model. So it helps us to define what the objects are that we are manipulating during problem solving. It also helps us to clarify some assumptions. What constraints are imposed by this model is clarified by writing down such a model. We can also use it to analyze requirements, so we can look at the representations we need to develop to represent the objects that we are manipulating during problem solving. Also, we can prove semantic properties with a theoretical device like this. The most important properties for algorithms we are interested in are soundness and completeness, and they require a semantic foundation which is given by a conceptual model. What a conceptual model isn't good for is developing efficient algorithms and other computational concerns. So we cannot immediately derive planners from the conceptual model. The conceptual model we are using in planning is called a state transition system. Formally, a state transition system is defined as a four-tuple consisting of four components S, A, E, and gamma. I will now explain these components in turn. The first component, S, is a finite or recursively enumerable set of states. So these are all the possible states the world can be in. This set can be finite or recursively enumerable, which means infinite. But in most of the examples we'll be looking at, we have only finite sets of states, so don't worry about the second part for now. The second component is a set of actions. Actions are the things an agent can do to change the state of the world. The third component is a set of events. Events can happen in the world and are not under the control of an agent, but events too can change the state of the world. The fourth and most complex component of a state transition system is the state transition function gamma. Gamma takes two things. It takes a state of the world as input, and it takes an action or event. So this second component is the union of all the actions and events, and one of those is the second argument to the state transition function. The result of applying the state transition functions then is another set of states. So this notation here, 2 to the s, just denotes the power set of all possible states, which means an element of the set is itself a set of world states. So the state transition function takes a state, an action or event, and gives us all the possible states that may be the result of applying this action or this event happening. We can now use this definition to define some other concepts formally. For example, applicability. We can say that an action A is applicable in a state S if gamma of S and A is not empty. So if there is at least one state that is the result of applying this action in the given state. And when we apply an action A in a state S, this will take our state transition system to a new state S prime, and S prime must be an element of gamma of S and A. Another way to look at a state transition system is to view it as a graph. Suppose we are given a state transition system S, A, E, and gamma, then we can define a directed labeled graph G that consists of nodes NG and edges EG. The nodes of this graph are simply the world states that are possible in this state transition system. So NG is equal to S. And the edges in this graph correspond directly to the state transitions defined by the state transition function. So we have an arc from a node S to another node S prime. So this is an edge in this graph, and that is labeled with label U, which is either an action or event, if and only if the state S prime is the result of applying U in S. U can be action or event. So we have a transition from here to here with label U. So a state transition graph consists of nodes that correspond to world states and edges that correspond to state transitions. Let me illustrate a state transition system with a very old problem that has been used many times in AI, the missionaries and cannibals problem. In this problem, we have a river, and on one side of the river we have 3 missionaries and 3 cannibals initially. The missionaries are black triangles and the cannibals are red circles here. There is also a boat available, and in this boat can be up to 2 people, and they can use this boat to cross the river. Now, the problem is, if the cannibals ever outnumber the missionaries on either of the banks of the river, then the missionaries will get eaten by the cannibals, and we don't want that. So you can see in the initial state there's an equal number of missionaries and cannibals on one side and no missionaries and cannibals on the other side, so there's no problem. The planning problem now is to come up with a sequence of actions that carries all the missionaries and cannibals safely across the river to the other side. This system can be described by a state transition system. And if you're not familiar with this type of system, I would advise you to now try to define this as a state transition system. Specifically, try to see what are the world states that are possible here, what are the actions, and what are the events that can happen in this problem. The state transition function is best defined as a graph, and if you sit down for about half an hour, I'm pretty sure you can come up with a graph that describes the whole state transition graph for this problem. So if you want to do this little exercise, you need to pause the video now. So here is my version of the state transition graph for the missionaries and cannibals problem. To define this as a state transition system, we have to define the 4 components. The first component is the set of states, S, and that can be defined as the different world states we see here. And these are all the squares, rectangles that are drawn here. There are 16 different world states, and they're denoted by these rectangles. So this is the initial state, as we've seen in the previous slide, where all the missionaries and cannibals are on the left-hand side of the river. And over here on the right, we have the gold state, and in this gold state, all the missionaries and cannibals are on the right-hand side of the river. The second component of a state transition system are the actions that are possible. In this case, there are 5 different actions, and I've denoted them here with the labels that occur on the different state transitions. So there's 2 types of actions, namely actions with 1 person in the boat and actions with 2 people in the boat. The actions with 1 person in the boat are the ones where we have 1 missionary or 1 cannibal in the boat. Or we can have 2 people in the boat. This can be 2 missionaries, 2 cannibals, or 1 missionary and 1 cannibal. It's noted here by 1M, 1C. So these are the 5 possible actions that we have to do something in the system. I don't need to denote where the boat is because the boat can only cross from one side of the river to the other. The set of events is empty for the state transition system. And finally, the state transition function is defined by all the arcs that make up the lines between the different states here. Note in this specific problem, all the arcs are bidirectional, which means with the same action we can go to one state and then back to the original state. So this is one arc here, and this is one, and this is one. And all these arcs together define the state transition function, and that concludes the definition of the state transition system. A state transition system is useful because it describes all the possible ways in which our system may evolve as a result of applying actions or events happening. But what we want to do is solve planning problems, and the solution to a planning problem is a plan. And by a plan, we mean a structure that gives appropriate actions that we can apply in the initial state of our problem, such that it gets us to a different state in which our objective that we're trying to achieve as part of the planning problem will be achieved. A simple example of such a structure would be to have a sequential list of actions that we need to perform in order. A more complex structure could be a function that maps states to actions, so that when we are in a given state we can use that function to decide what action to apply. A plan implicitly describes a path through our state transition graph. So when we execute a plan, we expect to end up in a state in which our objective is satisfied. There are different types of objective that can be defined for planning, and I will give you some examples now. The simplest way to define an objective is simply to have a goal state. This can be an individual goal state that is named. We've seen this in the missionaries and cannibals problem. Or it can be a set of goal states. That means one of those states is one that we want to reach. An objective can also include some constraints on intermediate states through which we are passing on our way to the goal. For example, we can have states that we don't want to go through, that we need to avoid as part of the objective. A more complex objective could also come with a utility function for each state and tells us that we have to maximize the utility on our way to the goal. As you can see, an objective can be quite complex. A completely different view of an objective would be to not try to achieve something, but to perform a given task. So a good example of this is when you are going on a holiday. You're not really trying to change the state of the world. You want to end up back in the same state where you started, but you want to do something in the time where you go on holiday, and that's a task that needs to be performed. Probably the most common reason for solving planning problems is that we want to execute the resulting plans. And here is a model for how plan execution might actually work. So we have a planner that is given a description of the state transition system that tells the planner how the world may evolve. We're also giving this planner the initial state, that is the state in which the world is in now, and some objectives that tell the planner where we want to be. The planner then solves this planning problem and generates a plan which is passed to the controller for execution. The controller takes this plan and executes the actions in this plan. So it has to extract the next action to be executed and passes this to the system. The execution of the action then changes the state of the actual system that we're trying to manipulate, for example, the real world. And hopefully our system is consistent with the description of the system that was given to the planner to generate the plan that we're now executing. But the system is not only changed by the actions we are taking, that are controlled by the controller, it is also changing because of events that are happening. For the controller to take appropriate actions, it usually needs to know what the state the system is actually in, and to do so, it has observations which are going from the system to the controller. We model observations through the observation function eta, which maps a state to a set of observations that can be made in this state. Quite often, the world is not fully observable, and in this case, the set of observations does not allow us to immediately infer which state we are in. So a given set of observation makes it possible that we are in a number of states. And this is what is called the belief state of the controller. Now, the model we've just seen is not very realistic, because the real world on which we are executing our plans is often different from the description of the state transition system that we're giving to our planner. So those two are not identical. The reason is that this description we're giving to the planner is an abstraction. It leaves out many details about the real world which make planning possible. And then when we execute the plan, things may go wrong because the two models are not the same. A more realistic model is called dynamic planning, in which planning and execution are actually interleaved. What is different in this model is that the controller has to do something called plan supervision, and that means it has to detect when observations differ from expected results. So it expects the world to be in a certain state as a result of an action, but it can observe that it isn't. What it can do in this case is plan revision. That is, we take the existing plan and try to change it in some way to take into account the new state. This can be done by the controller for very simple cases, or has to be done by the planner for more complex cases. In this case, the controller has to pass an execution status back to the planner so that the planner can generate a new plan that is passed to the controller and that takes into account the change that has happened. In the worst case, the planner will have to replan, that is, it will have to create a completely new plan from scratch for the given problem. Dynamic planning then closes the loop between the planner and execution by passing back the execution status to the planner for replanning or plan repair.